It's a pleasure to introduce Romain Tessera from Université. There is a misprint in the program. And he's going to tell us about coarse fixed point.
Thank you very much for the invitation. I'm glad to be back here. I was here in July. So I'm going to talk about fixed point properties. So before, I'm not going to talk about this coarse adjective right away. It's going to happen a little bit later in the talk. So I'm a little bit sorry for the fact that I'm not going to, my talk is going to sound a little bit exotic because it's not going to be a bit finitely generated, which it's not going to be interesting in the context of this talk. So, and what I wanted to say also, because all the results presented here are going to be a joint work with Jeroen Winkel. To quick math, unfortunately, recently, I tried to get him back, but it didn't work out. So he's in finance now, so he's making a lot of money. What can I do? Okay, so I'm going to talk about fixed point properties. So what's a fixed point property? So we take like a family of metric spaces. Of course, we are going to make assumptions on these metric spaces. And we say that a group definition, a group G has property fx if all isometric actions on space X in my family admits a fixed point. So in the case where I have a finitely generated group and my space is a Hilbert space, or the family of Hilbert spaces, then we get the property fh, which is well known and equivalent to property t. But other than that, we might assume that the spaces are not necessarily linear spaces, they might be Banach spaces. So one of the assumptions that we are going to make in this talk, although it's a little bit unfortunate that we need these assumptions for all the results, because there are also spaces which are not going to satisfy this assumption, but is the property of uniform convexity. So uniform convexity is generally well known for Banach spaces, but it actually makes sense outside of linear spaces. So I'm going to assume that X is a geodesic metric space or length space. So is uniformly convex if for all epsilon positive there exists delta, so these numbers are supposed to be small, such that we have an inequality which looks a little bit like what we have for linear spaces. So for all x, y, z, suppose that z is somehow thought as the center, like the origin in a Banach space, and you have x and y here. What you require is that, so because we are in a length space, in geodesic space, it makes sense to talk about the midpoint, or at least a midpoint, between x and y. So it will happen that from the definition, the space in question is going to be uniquely geodesic. We could add it, maybe. Let me add it, just to simplify the definition, although it's a consequence. So then, because it's uniquely geodesic, it means that it makes sense to define the midpoint, which is just the point which is at equal distance from x to y along the geodesic. And the property of being uniformly convex says that assuming that x and y are sufficiently far apart, then the distance from z of mxy has to be smaller than some explicit amount than the maximum distance from z to y. So I'm not going to write it down. We'll leave it to you as an exercise, because I gave you enough information, and it's a little bit annoying to write the details anyway.
We can invite 10 different definitions.
What?
We can imagine 10 different definitions in this data.
But afterwards, you can come to me and give me your definition, and I will tell you if it's the right one. So the point is that for banner spaces, it's equivalent to the usual definition. Now there is a motivation for working with uniformly convex spaces, which is the main use of this assumption in this talk is the notion of center, or circumcenter. So the circumcenter is the following thing. So before I write down the definition, assume that, so let X be a metric space. For now, I don't make any assumption. Metric space, and assume that, and let A be a bounded set, a bounded subset. So the circumradius of A, which is denoted by rho of A, is, roughly speaking, the maximum doesn't exist, but it's the minimum radius of a ball that contains the space. You have to take the infimum, obviously. So the way you can define it is just by writing that this is the infimum over all x in X of the supremum of all A in A of the distance between X and A. If you think about it for a second, you realize that if you remove the infimum, then there you're taking somehow the smaller ball that contains centered at the smaller radius centered at X, which contains all of A. And here you're trying to position it by taking the infimum so that this radius is as small as possible. Okay? So roughly speaking, intuitively, it's the rho of A is the minimum radius of a ball containing A. Okay? And the key lemma, maybe here, which is called the center lemma, which is, so the first instance of this lemma, I think so, we found it with Pierre, well, Pierre found it actually, is from 1901 for Euclidean spaces.
You mean in that formulation?
Yes. For Euclidean space. Yeah, it's more precise actually because it's a quantitative statement there. So here, and definitely not in this generality. Under the generality, I found it in a paper of Nika, but I'm not sure it's completely original. I mean, there are many people actually who reproved it in various settings. So I'm not going to give a list of names because I haven't prepared it very well. So the center lemma says the following thing, that if X is uniformly convex, then there exists a unique circumcenter namely there exists a unique X such that which realizes the infimum. So it means that there exists a unique ball of minimal radius containing your set A. Closed ball. Closed ball.
Does it mean that X is complete, or is it a consequence of that?
I'm not completely sure, so I will add complete.
Otherwise, you can just remove.
Yeah, no, right. Otherwise, you can remove the point. Yeah, sorry. It might not be geodesic anymore. So, yeah, it might, actually, I'm not sure you need it, but it's safer to add complete, just to be on the safe side. So, which is the infimum. Okay. So generally, the way it is used, although it's not the way it is going to be used in this work, but the way it is generally used is the following, through the following corollary. Assume G acts, G being any group, by isometry on such X with bounded orbits. Then there exists a fixed point. Okay, so just because somehow this unique, if you're fixed, if the orbit is fixed, then it also has to fix the circumstance. Okay. Yeah. So now I'm going to discuss. To discuss what we want to define if the group is not just simply a discrete group, but carries some extra structure. For instance, if G is a topological group. For instance, consider the case where G is locally compact. This is going to be a good guideline. Locally compact and compactly generated. Okay, so it means that there exists S, a compact generating subset. So here you have, when you have a topological group, the natural assumption to make is to define property FH. So is what we can call topological property FH. So G, which is now a topological group, has a topological FH, or Fx, sorry, if we have everything for continuous sections. Okay, continuous sections. But now, in our example, where we have a locally compact group equipped with a compactly generated, generating subset, there is an alternative definition which makes sense and seems quite reasonable, which is not necessarily to assume that the action is continuous, but to assume that the compact generating set, or any compact set in G, moves points the orbit of compact subsets are bounded. Okay, so And so why is it interesting? I mean, one reason for considering these actions is that when you consider ultra limits of actions, it's generally easier to control this data. The fact that in the ultra limits, you also get the same property. Although getting continuity requires more work, as Michael knows. It can be done for ultra limit of actions on Banach spaces, but if you go beyond Banach spaces, it can be, I mean, I don't necessarily know how to deal with it. So that's one motivation. And one, so now let me define the correct setting which is the notion of Bornological groups. I'm going to give you a bunch of examples. Most of them, at least in this talk, are going to be locally compact groups. But anyway, there will be other ones as well. So Bornological groups, what is a Bornological group? So the definition, it's, so a Bornology is a set, a family of sets of so-called bounded sets. So so it's a family which bounded sets with which has to satisfy the following properties. So we want the singleton to belong to it. We want it to be because bounded is a way of saying that the sets are relatively small. So we want that if A is contained in B and B is bounded, then obviously A is bounded as well. And finally, we want some compatibility with the group thing. So we want that if A and B are bounded, then we want that the product of the two are bounded. And we also want that the union is bounded. And that's it. And then you can define from a Bornology, you can on a group, you can define a left invariant core structure, which I'm not going to define, but it's easy to understand. So, which you can think of as some generalization of a left invariant metric, okay? Because bounded are going to be the sets which are bounded for this metric, and that's of course one example. So, and now assuming that if G is a topological group, and this has been quite studied actually in the context of Polish groups. There are two natural Bornology. So one of them, which is generally called, which is generally denoted kappa, is just the set of precompact sets. And that's the one which corresponds to this notion of, I mean, for compactly generated locally compact groups, that's the one that we get naturally when we discuss what I've informally described earlier. And another one, in order to introduce it, actually I need just to mention something. So whenever, so for all isometric action, sigma continuous, sorry. Actually, you don't need necessarily continuous, but isometric action of G over a metric space, you can define a Bornology which is naturally associated to it, which is just, you define B sigma to be the set of B and G whose orbits are bound. It doesn't depend on the orbit. One of them is bounded, and they are all bounded. So
X has its own topology. Oh.
X is a metric space, isometric action. And so from there, you can define what's called OB, which was defined by Rosendahl, which is just the intersection of B sigma for all continuous isometric actions. And so this is a quite naturally defined thing. And it turns out, which it's not hard to see, that for sigma compact locally compact groups, the two coincide. And for compactly, and yes, so that's for compactation of the group, it corresponds to the core structure associated to a Cayley graph of associated to a compact generating set. Okay, so there are three sources of examples that we consider in our work. So that we have considered. I'm not saying that there are not much more, but somehow the ones which we have been interested in are the following ones. So one are locally compact groups, as I said, for which we can deduce, for which our results have implications which are new, so I'm going to talk about it in a minute. And the second one are specific, families of Polish groups for which we prove certain fixed point properties. I'm not going to describe it in this talk, but I'm just mentioning it to you. You can find it in the paper. For instance, this one, which is the set of homomorphisms of R, which are lifts of homomorphism of the circle, or if you want, because this group is interesting because it's a central extension of the group of homomorphism of the circle, and as a Polish group, it is bounded in the sense that all isometric actions are bounded, but not for this one. So this one has the same coarse geometry as Z, but still we prove that it has some fixed point property, like property T property. Okay. But I'm not going to talk about this in this talk. It's just to advertise it. Sorry, because I don't have enough time. And the third example comes from, so it's a natural bornological group, actually topological and bornological group, which is not Polish. And this I'm going to talk about it, arising from sequences of Cayley graphs, of groups, of finite generative groups. Okay, so maybe. Yeah, so I'm going to state a theorem which plays a central role in what I'm going to say later. And this theorem, which is 23, is a theorem about automatic continuity somehow. So I should call it looking for continuous subactions. So you take G, a topological group, an arbitrary topological group. Okay, and consider an action, not continuous action, an action by isometries on X, where X is uniformly convex. And we make an assumption on the action which says that for somehow the action is kind of bounded, I'm going to tell you exactly what, on some open sets, and we are going to deduce the existence of a whole convex closed subset of X on which the action is continuous. Okay? So precisely the statement is let U be an open neighborhood of the identity. Okay. And C be a constant such that there exists X, well, maybe I should put X somewhere, C and X, such that the orbit of U is bounded by C, meaning that the distance of Gx, X, is less than C for all X in, for all G in U. Okay? So you have somewhere a point X where the U orbit of X has diameter. It's not exactly diameter, it's a bit more precise, but roughly speaking, is bounded, okay, by C. Then the conclusion, so that's the assumption, okay? So the conclusion, there exists Y, another point, which lies not too far from X. It's important, especially the fact that it lies not too far from X. It's important more for coarse properties applications than for coarse fixed point properties. But still, I think it's important to mention it. So Y at distance to C from X, such that the restriction of the action to the closed convex in a sense geodesically convex subspace G invariant. Generated by X, by Y, sorry, is continuous. So the space is just a closed convex hull of Gy. It's another way to say it. Okay? And if the metric space is a Banach space, then you can take, instead of the convex hull, you take the linear space spanned by it. Okay? So of course the main point is to find Y on which the action is continuous. Once you have it, the fact that it passes to the convex hull and so on, it's not completely obvious. It also uses a convexity, uniform convexity, but it's not the interesting part of the statement. So because I think that, because this result has most of our applications, I'm going to explain a little bit how it is proved. It's also fun, I think. It's going to be probably the funnest part of my talk. I'm not going to give all the details, but I'm going to give you the idea, which is quite simple and cute. Sketch of proof. So, papers. So it relies on a lemma about this circumstance center that I introduced, which is still defined, I think, somewhere. So the lemma says the following. So suppose X is uniformly convex. Okay. And suppose that you have two sets. Yeah, so for all epsilon, there exists a constant C that depends on epsilon, which can be small or large. I don't remember if the problem is when it's small, I think. But we don't care, which is positive. Such that for all pairs of bounded sets, one being contained in the other, we have the following inequality, which is the distance between the circumcenters of B and A is controlled by epsilon times the circumradius of A plus a constant, depending on epsilon, of the difference between the two. A here and B here. Okay. It's a positive number because B is contained in A. Okay. So what does it mean? So I'm not going to prove this lemma. This lemma is proved using uniform convexity. And of course, I mean the C epsilon depends on uniform convexity modulus, which is the way delta depends on epsilon. Okay. And so the key of this lemma, it says that if B is very close to A in the sense that rho of A is very close to rho of B, then you can make this difference small, roughly. You know, you have to maneuver a little bit. Find first fix your epsilon and then make A very close to B. But roughly speaking, the idea is that if you have two sets A and B which are very close to one another, the centers also are quite close. So now how do we proceed for the proof? The idea is to find, okay, so in order for the proof, so we assume first that G is not discrete because otherwise it's not very interesting, okay? Because the actions are all continuous. And so then we can find, I mean, you have to prove it, but it's well known and it's easy that, so then we can find a family of a neighborhood of open sets, neighborhood of the identity, which are all contained in our U here, and indexed by the unit interval, satisfying that Vt is contained, strictly contained in Vt prime when T prime is bigger than T. So it's a family of distinct neighborhood of the identity which are strictly contained in one another, and they are all contained in U. So we start with this, and now we just consider the function, which goes from t to, so you fix x is the x which is coming from the theorem. So we look at the radius of Vt applied to x. Okay. So that's definitely, because Vt is an increasing family of subsets of G, I mean, this is an increasing function. Okay. It's an increasing function, a non-decreasing function. And being non-decreasing, it has a continuity point. Okay. And now the idea, I'm not going to write the details, but you can easily guess how it goes, that we are going to combine this with the lemma to say that, well, if I take this T0, then if I look at the circumcenter of Vt applied to X, so by the lemma, and writing a few lines of calculus, we have that the action is continuous in restriction to the orbit of that point. G1. Okay? The idea really is that because the fact that I'm taking a continuity point of this function, it means that at Vt0 is not going to move too much, and so the centers are not going to move too much. Roughly, that's the idea. Okay? Using this lemma. So that's the proof. Here's the sketch of the proof. And now how do we apply this?
You don't assume that the group is complete?
That the group is complete?
Yes.
No. I don't think we need.
The first line implies that G is uncountable. If you have. But,
If you take Q,
but
no, I'm not sure. For Q, you can. Well, let's discuss it afterward. I don't think so, because for Q you can Q with the topology of R. You have this family, so I'm not sure you need it actually. So in any case, we are going to apply it to the case where the groups are locally compact. But now I think the proof doesn't use it. So I hope it's fine, but I have all the things in mind. So. So first of all, let me just go back to the bornological groups, because I haven't defined yet this notion of coarse fixed-point property. So first of all, I need to define what's an action which is compatible with the bornology. So assume that you have an action, an isometric action, on a metric space. So isometric action of a bornological group. We say that the action is called control if for all bounded sets the orbit is bounded. If we want to be a little bit fancy, it means that we are requiring that the bornology is contained in the bornology of the action theta. Which is the bornology I was defining. Earlier I was defining it for continuous actions, but here we don't have even a topology here, so a priori. Okay, so now that we have this definition, we can define, that's not very exciting, but we can define for a bornological group and for a family of metric spaces, so coarse property F. Is just restricting to now not for continuous action, but for control actions. So if you want one of the main, a corollary. Yeah, well, so first, in order to have applications, nice applications, or at least, significant applications of these results here, the idea of these applications, if you want, is that this is something I've I've sketched before is the fact that when you deal with ultra-limits of actions, it's much easier to control the fact that the limit action is controlled. Okay? To make sure that the limit action is controlled. Making sure that the limit action is continuous is more tricky. And so, but also for that reason, the property fx that we are going to consider is going to be for families of metric spaces X, which satisfy certain conditions, which I'm going to call the standard assumptions on the families X. So one, I'm going to assume that these are all uniformly convex. Not necessarily uniformly over all of them, but I'm going to assume that the family is stable under various things. So closed convex subsets. This is obviously a consequence of the theorem, somehow, the fact that we want to use the theorem. Or you can replace it by linear if you are in the context of Banner spaces. And stable under rescaled ultra-limits, which I'm not going to define properly here. It's not the point. I mean, you can easily guess if you know what an ultra-limit is. It means that you are allowed to rescale the distance and that you are allowed to take ultra-limits, counted ultra-limits. So for instance, but I'm going to give you examples of the metric spaces which... Excuse me?
Doesn't it imposes uniformity on the uniform convexity?
It does, actually, automatically. It does automatically, thanks. Actually, it's true. So maybe some of the examples are going to be, all uniformly convex spaces with a uniform modulus of convexity. And here you may take uniform space or Banner spaces, potentially. You may take all closed subspaces of LP for, let's say, some given P, fixed P. Fixed P in 1 infinity. We are not allowed to take 1, which is a little bit unfortunate, but. And let's say cat-0 spaces. That's another family, an interesting family of examples. Or you may take R trees, for instance, or finite products. No, not finite products, you need subspaces. So let's say R trees. That's a list of examples. You could cook up other ones, but and now for these families under these standard assumptions, we have the following corollaries. So the first corollary is of the theorem which I erased, which was a bad idea, but anyway, is the fact that for sigma compact, locally compact groups, coarse property fx is equivalent to topological property fx. So it's a direct consequence of the theorem, which I erased. So coarse means here for the Bornology, which is K or OB, or the way they are the same. So it's not a big deal to. And this has the following application. So this is still is still a result which mentions this coarse property, but now you have also corollaries which do not mention coarse properties, which are purely in terms of continuous actions, like the following one. I'm going to tell you who have proved this result under certain assumptions. So, something I forgot to say is that X satisfies the standing assumptions. So same thing, X also satisfies standing assumptions. So if G is locally compactly generated with property Fx, then continuous property Fx, topological compact. Then there exists a compactly presented group G tilde, which surjects also with property Fx, which surjects to G, the continuous morphism, whose kernel is discrete. Okay, so it's the end. So you probably know this result, which was already originally stated by Shannon, for discrete groups, which says that when you have a finitely generated group with property T, then there exists a finitely presented group with property. You can truncate the presentation. If you go far enough in the presentation, then it's going to have property T. So that's the analog. You can work with the notion of marked groups in the context of locally compact groups, compactly generated. The only thing which is a little bit annoying that you don't have a notion of a free group in this situation, but it's okay. You just fix. Well, you can do it. So you can prove it. So the problem of this so this result also has been proved by Michael for actions on banner spaces. The difficulty to adapt the proof is in the fact that you want to at some point you have to work with an ultra limit action, and you want that the ultra limit action is continuous, and here we can get it even for actions for fixed point properties on non-linear spaces. I don't know if there is any other way of doing it. So there are other results of that form. I don't know if I have some time. I have 11 minutes. Maybe I should not spend too much time. So another result of the same form, which again doesn't mention coarse properties, is the fact that which is also a result of Shalom for discrete groups, even for locally compact groups for property property T, it's due to I will tell you. So assume that G is locally compactly generated again, and suppose that it has the following property. That all isometric continuous sections then G has topological Fx. So this is in the context of property T. So when X is just Hilbert spaces, this can be formulated in terms of first cohomology. It tells you that if a group, if your group is such that all its continuous representations have trivial reduced cohomology, first reduced cohomology, then it has trivial cohomology. Okay, and that was proved again by Shalom, and it relies on the same type of limit arguments. Okay, and so again you have it for, and this also was proved by Michael for actions on banner spaces. This is the same type of methods. Okay, so in the...
Romain, if you could stop 5 minutes before so that we have time for discussion.
All right. Yeah, because now it should... Oh, maybe I can stop here, actually.
Well, it's up to you, but...
Yeah, well, if you want me to tell you about sequences of expanders and stuff, I can.
I will ask questions.
I leave it to you. But then I will stop now.
Thank you very much.
So anyway, I plan to ask you number 3, so natural topological group arising from sequences.
Okay, so let me just tell you quickly what is the group. So suppose that you are given a sequence of Cayley graphs. With given, let's say that you have a family of finite generating sets of fixed cardinality, simplify, and you consider the following group, G, which is just, it's called the bounded product, so it's just the families gamma n such that it's a very simple group, but it's a big group somehow, you know, which has a natural generating set which is composed of the product of, so there exists a generating set of G, which is just the infinite product of Sn. Okay. So this infinite product of Sn defines the bondology. Okay. It's just the distance. It's associated to the Cayley distance associated with this set, but it also comes with a topology. And the topology, you fix any proper function. So proper meaning tends to infinity, and you define U rho, which is going to be a family of neighborhoods of the identity, to be Gn such that which are in G, but such that the size of Gn is less than rho of n. So rho is tending to infinity, so it's kind of a way of filtrating somehow. So this defines the topology, and for this topology, you get that this topology is quite natural in the sense that it's a proposition, let's say, like we have that the bondology here is the same as, like for compact groups, it's the same as, so the bondology I've defined is completely compatible with this topology in the sense that it gives you exactly the same bondology as the compact one or the OB one. And now the thing which is interesting is that I'm going to do it quite quickly. So assume that the gamma n are finite. Then we have that the family of gamma n Sn is an expander. And it's not completely obvious if G has topological T. Or T, it's the same. You can cook up a definition for T which is equivalent. And you have that, and if you require coarse property FH, then it's stronger. You get that has, so G has coarse FH, if and only if there exists a gamma with a gamma S with T, which surjects to all gamma n simultaneously, where the map send the generating set to Sn, And this is equivalent to the fact that the box space here that has geometric property T in the sense of U and willets. So somehow
is there a relation between gamma and G?
Yes.
Gamma and G, not clearly. No, not really. You can view G. G has a G subjects to. Yeah, G has a surjection to gamma. This is true. Which maps the generating set of G to the generating set of gamma. So yes, there is a relation. G is some kind of big object which lives above them. So, but it's interesting somehow. I don't know if it has application, but at least, I mean, this result is new, but probably not really new in the sense that if we let NU wanted to prove it, probably they could do it. But at least what I think it's interesting in terms of the point of view that gives us on this on the difference between this being an expander and being a geometric expander, which is much stronger, which is. That was a long answer. Sorry.
Any other quick question?
Yeah.
Maybe in this left theorem you have a characterization and when G has fx or x.
No. No, because it uses. The thing is that. The thing that we were actually, I would have to think about it a bit more because originally we were actually interested in the geometric property T, which now has a Van R version actually. So we wanted to prove that, we wanted to see whether this geometric property was related to our notion, and that's what we discovered. But so we didn't think about this equivalent statement here, which could be indeed true. That this equivalence between the two could be true.
It was more
From G, from
first
G.
statement.
The first statement. For the first statement also. Yes, I don't know. The first statement is a little bit tricky, so I'm not sure it will work, but I would have to think about it.
More questions? Doesn't seem to be the case, so let's thank Romain again.